Hello guys, welcome to another session. In this session I want to solve another problem in heat transfer. But first let me introduce a reference. This is heat transfer 10th edition from Mr. J.P. Holman. Okay, let's go to page 62 for solve another problem. Okay, so I'm gonna solve this problem number 16. Problem number 16, as it said, a spherical tank 1 meter in diameter, let me highlight it, 1 meter in diameter, is maintained at a temperature of 120 degrees Celsius and exposed to a convection environment with H is 25 watt per meter square degree Celsius and T infinity is 15 degrees Celsius. What thickness of urethane foam, kind of insulated, should be added to ensure that the outer temperature of the insulation, it means outer temperature of urethane foam, because this is kind of a sphere form, does not exceed 40 degrees Celsius. Okay, what percentage reduction in heat loss result from insulating this insulation? Okay, let's solve this problem together. Okay, first I want to draw a picture of this sphere, which diameter of that is 1 meter, and this would put into an environment which is convection. The temperature of that at the first is 120 degrees Celsius, which this would be T of wall. Okay, and H here is, as the problem said, 25 watt per meter square degree Celsius, and the T infinity temperature of this environment, water maybe, will be 50 degrees Celsius, which is T infinity. Okay, we want to put it inside, we want to add, actually let me draw this picture again. Again, that environment, that sphere, again 120 degrees Celsius, and the difference between number 1 and 2 is we want to add an urethane foam thickness around the sphere, and the temperature shouldn't be the temperature of this wall, as the problem said, shouldn't be T wall 2 shouldn't be more than 40 degrees Celsius. Okay, we want to solve this problem. And T infinity, again, that doesn't different, 50 degrees Celsius, T infinity, and H the same, all the same. So we want to let me write material, urethane foam. Okay, urethane foam. This layer is Orathon film around the sphere. Okay, let's solve this problem. First, in this situation, we want to know and evaluate Q. Okay, all the energy of that. So it would be HA delta T. Which delta T? Let me write it. 20. Okay, let me write instead of delta T infinity minus T wall. Okay, so H is 25. A, as you know, area of the sphere will be 4 pi R2. Okay, 4 pi R2. We have R of this sphere, and multiplied by T infinity minus T wall. Okay, it would be 25 again. 4 pi, and our I is in meter, of course, square T infinity. Sorry, I have to write it opposite of that. T wall minus T infinity, because T wall is greater than T wall. Otherwise we need a minus here. T wall minus T infinity. Okay. Then T wall is 120, and temperature, infinity temperature, is 15. Okay. Then Q would be eight. Q would be 8,247 watts. Okay, this is value of Q. Okay, then this is our Q from this one, but we just have this Q here. But as we know, we want to evaluate. For example, imagine this layer foam of thickness. It would be this one. Okay, we have a Q inside this section, this which is 8,247 watts, and this Q will be out again. Okay, but the formula is not the same as this formula. This is different. We want to write the formula for this one. Let me go to the PDF and go to the equation 210 in page 31. Okay, for these sections we have this formula. Okay, we want to write this formula and evaluate Q for this section of sphere. Okay, then let's do it. I want to write formula for this one. It would be Q equals 4 pi K, which is thermal conductivity of this material, and we know K will be 18 multiplied by 10 minus 3. Okay, watt meter degree Celsius. 4 pK Ti minus TL 1 over R in minus 1 over R out. This is R in, R out, and this is R in. Okay, we should put all of these value inside the formula and evaluate it. Okay, if we do that, this would be equals to 8,247, okay, watts. Then 4 pi 18 multiplied by 10 Ti, we know temperature of this point, which is Ti. Ti equals 120 degrees Celsius, okay? And this T shouldn't be more than 40 degrees Celsius. This is T out, okay? Let me write it in our formula. 120 minus 40, okay? Divided by Ri, which is this diameter. Let me write it in radius. 0.5 minus, I don't have R out and I want to calculate it from this formula, and after that calculate the thickness of Oraton film. Then it equals okay 8,247. Okay, if we calculate, we have just one variable. R out would be 0.02 meter, okay? But we want to know R O minus Ri, okay? We know it. O2 minus O, it would be obvious, it is 20 millimeters, okay? Then thickness would be 20 millimeters. This is the first section of the question, but the second for the question would be, let me go back to the PDF. What percentage reduction in heat loss results from insulating this formula? Okay, it is, let us calculate it. We know 19, if we calculate Q 78 watts, if we minus 8,247 minus 1978 and divide it by this number again, multiplied by 100%, it would be 76%. The second second section of the problem would be like that. For knowing this 1978 watts, we should, if we assume we don't have this Oraton film, but we have a medium which the temperature is 40 degrees Celsius, okay? So if we calculate Q, sorry, I will again write it. It will calculate Q, H, the same as H before H, A, the same, but delta T is different, 120 to 40 degrees Celsius, okay? It would be something like that, okay? And the loss, it would be actually 8 to 47 minus 1978. Okay, this is the loss of heat. This is the loss of heat. We don't have it in this situation. Okay, so if we do want to know about the percentage of loss, saving energy, this is 76% of previous one. Okay, this was the answer of this question, but you should think about it and do it by yourself to know exactly what is happening in this problem and know about all details. So let's do it, and do it by yourself. And thank you for watching this session. I hope you enjoyed that. Take care and bye bye.